In this video, I'm going to go over some examples of solving trig equations. And to solve trigonometric equations, it is crucial that you know how to evaluate all 6 trig functions at the angles 0, pi over 6, pi over 4, pi over 3, and pi over 2, along with their symmetric counterparts that you see in this picture on the unit circle. Let us start the first example by solving the equation 2 sine x minus 1 equals 0. So start solving the equation by adding 1 to both sides to get 2 sine x equals 1. Dividing by 2 on both sides, we get sine x equals 1/2. And for what angles is the sine function equals 1/2? Well, remember that the sine x is periodic with period 2 pi. So within that period, at pi over 6 radians and at 5 pi over 6 radians, sine is equal to 1/2. So we have x equals pi over 6 plus 2k pi, or x is 5 pi over 6 plus 2k pi. K is an integer. And that is the general solution to this equation. Next example, let's solve the equation cosine x plus root 2 equals minus cosine x. If we manipulate this equation by moving minus cosine x to the left side of the equation and root 2 to the right side, we get that 2 cosine x equals minus root 2. Dividing by 2, we get cosine x equals minus root 2 over 2. And for what angle x is the cosine equals minus root 2 over 2? We have exactly 2 angles. The first one is 3 pi over 4. And the second one is 5 pi over 4. The cosine of these 2 angles equals minus root 2 over 2. And this comes from this picture right here. So you can see that at 3 pi over 4, the cosine is minus root 2 over 2, and at 5 pi over 4, the cosine is minus root 2 over 2 as well. So going back to our equation, and keeping in mind that cosine x has a period of 2 pi, we get that the general solution to our given equation is x equals 3 pi over 4 plus 2k pi, or x is 5 pi over 4 plus 2k pi. Of course, k is an integer. In the next example, we solve the equation 3 tangent squared x minus 1 equals 0. So let's start out by writing 3 tangent squared x equals 1, which means that tangent squared x equals 1/3. Square rooting both sides, we get that tangent x is 1 over root 3, which is the same as root 3 over 3 if we rationalize the denominator, or tangent x equals minus 1 over root 3, which if we rationalize, we get minus root 3 over 3. Now keep in mind that the tangent x has a period of pi. So for what angle between 0 and pi is tangent x equals root 3 over 3? Well, there's one angle, namely pi over 6, where tangent x equals root 3 over 3. So this tells us The first equation, tangent x equals root 3 over 3, gives x equals pi over 6 plus k pi. As I said, the tangent x function has period pi. That's why we put k pi. And tangent x equals minus root 3 over 3 has exactly one solution between 0 and pi, namely 5 pi over 6. Notice how in the second quadrant the tangent is negative. So this tells us that x equals 5 pi over 6 plus k pi. Of course, k is an integer. So the general solution to the equation 3 tangent squared x minus 1 equals 0 is x equals pi over 6 plus integer multiples of pi, or x equals 5 pi over 6 plus the integer multiples of pi. Next example, solve the equation 4 sine squared x minus 3 equals 0. So 4 sine squared x equals 3. Sine squared x equals 3 over 4. Taking the square root on both sides, we get that sine x equals square root of 3 over 2, or sine x equals minus square root of 3 over 2. Now let's find the angles x for which sine x equals root 3 over 2. In the interval from 0 to 2 pi, there are two angles for which the sine is root 3 over 2. Let's go back here. For which angles is sine x equals root 3 over 2? Well, we have 60 degrees, or pi over 3, and 120 degrees, or 2 pi over 3. This is when the sine equals root 3 over 2. So we go back. The first equation gives the solutions. X equals pi over 3 plus 2k pi, or x equals 2 pi over 3 plus 2k pi. Of course, k is an integer. Pi over 3 and 2 pi over 3. Let's move on to the second equation, sine x equals minus root 3 over 2. There are two angles for which sine x equals minus root 3 over 2, namely 4 pi over 3 and 5 pi over 3. So the second equation gives x equals 4 pi over 3 plus 2k pi, or x equals 5 pi over 3 plus 2k pi. In all of these four cases, k is an integer. So the general solution of 4 sine squared x minus 3 equals 0 is x equals pi over 3, 2 pi over 3, 4 pi over 3, 5 pi over 3, plus the integer multiples of 2 pi. Next example, let's solve the equation cotan x times cosine squared x equals 2 cotangent x. We start by moving 2 cotan x to the left-hand side to get cotan x cosine squared x minus 2 cotan x equals 0. Factor out cotangent x to get cotangent x times cosine squared x minus 2 equals 0. This means that cotangent x equals 0, or cosine squared x minus 2 equals 0. To solve cotangent x equals 0, keep in mind that the cotangent has a period pi, and cotangent x is equal to 0 precisely when cosine x equals 0. That's because cotangent x is cosine x over sine x. Now, cotangent x is equal to 0 at pi over 2 in the interval from 0 to pi. So to solve the first equation, cotan x equals 0, we have x equals pi over 2 plus k pi. K is an integer. Let's move on to the second equation, cosine squared x minus 2 equals 0. Well, that's equivalent to cosine squared x equals 2, which in turn is equivalent to cosine x equals plus or minus square root of 2. Now, square root of 2 is roughly 1.41. So that's roughly plus or minus 1.41. Now, these equations have no solutions because cosine x is always trapped between minus 1 and 1. So there's no way cosine x could equal root 2 or cosine x could equal minus root 2. So the general solution to our equation is x equals pi over 2 plus the integral multiples of pi. Next, let's solve the equation 2 sine squared x minus 3 sine x plus 1 equals 0. So this is a quadratic equation in sine x. We can make a substitution. Let u equals sine x. And with that, our equation becomes 2u squared minus 3u plus 1 equals 0. To solve this quadratic equation in u, we can factor first. And to do that, we need two numbers that multiply to 2 and add up to negative 3. Well, negative 1 and negative 2 do the trick. They multiply to 2, add up to negative 3. This means our equation, or our quadratic expression on the left, factors as 2 u minus 1 over 2 u minus 2 over 2 equals 0. Let's simplify. 2u minus 1 half u minus 1 equals 0. To solve this equation, this means that u equals 1 half or u equals 1. But remember, u is sine x. So we have sine x equals 1 half or sine x equals 1. Let's find out the angles for which sine equals 1 half. There are two angles within the period of sine x, which is from 0 to 2 pi, for which the sine is 1 half, namely pi over 6 and 5 pi over 6. So our first equation gives rise to x equals pi over 6 plus 2k pi, or x equals 5 pi over 6 plus 2k pi. Next, let's solve the equation sine x equals 1. Well, sine x equals 1 exactly when x equals pi over 2. And that's the only angle between 0 and 2 pi, the period of sine x, for which the sine equals 1. So the second equation gives rise to x equals pi over 2 plus 2k pi. In all of these cases, k is an integer. Next example, let's solve the equation 3 secant squared x minus 2 tangent squared x minus 4 equals 0. We start out by recalling the following Pythagorean identity. That secant squared x is equal to tangent squared x plus 1. So I'm going to replace the secant squared x with tangent squared x plus 1 to get 3 tangent squared x plus 1 minus 2 tangent squared x minus 4 equals 0. This gives 3 tangent squared x plus 3 minus 2 tangent squared x minus 4 equals 0. Collecting like terms gives tangent squared x minus 1 equals 0. Tangent squared x equals 1, which means that by taking square roots, tangent x equals 1 or tangent x equals minus 1. Keeping in mind that pi is the period of tangent x, let's solve the equations tangent x equals 1 and tangent x equals negative 1. Now, for what values of x is the tangent equal 1? There's exactly one value between 0 and pi for which tangent x equals 1, namely at pi over 4. So the first equation tells us that x is pi over 4 plus k pi. And the second equation, tangent x equals negative 1, gives rise to one solution in the period 0 to pi, namely at 3 pi over 4. In other words, tangent of 3 pi over 4 equals negative 1. So the second equation gives rise to x equals 3 pi over 4 plus k pi. K is an integer. And that's the general solution to our equation. Lastly, let's solve the equation cosine x plus 1 equals sine x in the half open interval from 0 to 2 pi. As it stands, there's not much that can be done to solve the equation cosine x plus 1 equals sine x. So the trick to do it is to square both sides. If we square both sides, we get that cosine x plus 1 squared equals sine squared x. The idea here is that the solutions to cosine x plus 1 equals sine x must be among the solutions of cosine x plus 1 squared equals sine squared x. So if we can find the solutions to this equation, the solutions to our equation cosine x plus 1 equals sine x must be a subset of the squared equations, of the solutions of the squared equation. So let's proceed solving cosine x plus 1 squared equals sine squared x. Expanding on the left, we get cosine squared x plus 2 cosine x plus 1. On the right-hand side, I'm going to use a Pythagorean identity. The Pythagorean identity that sine squared x equals 1 minus cosine squared x. So I'm going to replace sine squared x with 1 minus cosine squared x. Moving everything to the left-hand side, we get that 2 cosine squared x plus 2 cosine x equals 0. Factor out a 2 cosine x. We have 2 cosine x times cosine x plus 1 equals 0, which tells us that cosine x equals 0 or cosine x plus 1 equals 0, which tells us that cosine x equals 0 or cosine x equals negative 1. Remember, we want to solve these equations in the half-open interval from 0 to 2 pi. So, cosine x equals 0 or cosine x equals negative 1. We want those in the interval from 0 to 2 pi, the half-open interval. Cosine x equals 0 is equal, cosine x equals 0 precisely at pi over 2 and 3 pi over 2. These are the only angles where the cosine is 0. So the first equation gives x equals pi over 2 or x equals 3 pi over 2. Cosine x equals negative 1 has exactly one solution in the half-open interval from 0 to 2 pi, namely at pi. So cosine x equals negative 1 gives x equals pi. These are the solutions to the squared equation, namely to cosine x plus 1 squared equals sine squared x, which is not our desired equation. Our desired equation is cosine x plus 1 equals sine x. But we know that the solutions of our desired equation, cosine x plus 1 equals sine x, are a subset of the solutions of the squared equation, namely pi over 2, 3 pi over 2, and pi. So we're going to check these numbers one by one to see which one of them or which ones satisfy our desired equation. So we have our equation cosine x plus 1 equals sine x, and we would like to check which one of those numbers, pi over 2, 3 pi over 2, and pi, which one of those numbers satisfy our equation. Let's start out by checking x equals pi over 2. We plug in pi over 2 for x, and that gives us the following. The left-hand side of the equation, LHS stands for left-hand side, would be cosine pi over 2 plus 1, which is 0 plus 1, that's 1. And if we plug in pi over 2 on the right-hand side, we get RHS, right-hand side, equals sine pi over 2, which equals 1. Notice that the left-hand side equals the right-hand side, so x equals pi over 2 is indeed a solution. Next, let's check x equals 3 pi over 2. The left-hand side gives cosine 3 pi over 2 plus 1, which is 0 plus 1, and that's 1. The right-hand side is sine 3 pi over 2, which is negative 1. Notice the left-hand side and the right-hand side are not equal to one another, so x equals 3 pi over 2 is not a solution to our equation. Cosine x plus 1 equals sine x. Finally, let's check if pi is a solution to our equation. The left-hand side is cosine pi plus 1. That's negative 1 plus 1, which is 0. And the right-hand side is sine pi, which is 0. Left-hand side equals right-hand side, so x equals pi is a solution. Therefore, the solutions to our equation cosine x plus 1 equals sine x in the half open interval from 0 to 2 pi, they are x equals pi over 2, this comes from here, pi over 2. We rule out 3 pi over 2, and the other solution is x equals pi.